Okay. Okay, so well, good. Okay, I think we can get started. So we're going to talk about, can you hear me in the back? Let's see. Okay. Okay, so we're going to talk about cache design and management. Everything's good? Okay, online as well. Cache design and management, building on what we did last week. We started caches, if you remember. We talked about memory organization and technology, and the memory hierarchy, and then caches. Today, we're going to go a little bit more deep into caches. This is an area where a lot of work has been done for many, many decades. As I mentioned last week, the earliest cache paper was in 1962, right? That's 60 years ago. But much better. That's 60 years ago. And over the course of 60 years, a lot of work has been done and a lot of different things have been explored. I'm just going to give you a glimpse of it today. There are a lot of design decisions. The memory hierarchy, this is one of the most complicated parts of a system today, how to do the caching. And it keeps getting bigger and bigger, as we discussed earlier. So you'll get a glimpse of it, but know that there is a lot to do when you're implementing a cache hierarchy or memory hierarchy in a real system. Okay, so hopefully you know about the extra assignments. These are the same readings that I've been showing for many days, let's say. And just to jog your memory, this is what we're talking about, the memory hierarchy of a modern processor. We'll keep talking about that until the end of the semester. And this is another example of it that includes the registers as well as the solid state drives today. I should mention that this memory extends. So this is, if you think about it, this is a single node. A single node has this memory hierarchy and then a storage unit and then main memory, as you can see over here. But this memory, don't think that this memory is just for a single node. In modern data centers, for example, or servers, you can extend the main memory hierarchy beyond the single machine. So in some cases, you need to store much more data than what you can do attached to a single node, like this node, let's say. So what happens if you actually need more data to store? Then you actually go to some other machine. And this could be an example, basically. You could have a compute node over here that's local, and it has its own local memory and local hierarchy for memory. And then you attach some remote memory node, which could be essentially the same as this node, or it could be different. It could be designed just to store data for memory. I will show you an example of that later on. In this case, they look kind of similar, basically. You have a compute node, maybe another compute node that has memory, and then you share memory. You put some of the memory that you don't access to this remote memory, and when you need to access it, you bring it to your local memory. Basically, the benefit of doing so is to enable even higher memory capacity, because you're limited by how much memory capacity you can have in a single node due to the pin limitations that we discussed, right? With a given chip, you can have only some number of pins. You can extend that with having more channels, for example, and in each channel you can have many ranks, for example. But in the end, you push the limits of power and physical limits and cost limits in a single compute node. So you may need to actually go to the go over the network to some other node to have some more memory. And this is what's real in modern systems, actually. In modern data centers, for example, when you have lots of data and you need to access lots of data, you have these memory nodes. So let me give you an example so that you don't think that memory is something that's just local to your machine. This is a system. This is from a paper that was written about 11 years ago, as you can see. You can see that this is a system with memory blades. You have some compute blades and you have some memory blades, and they're connected to each other via some network. They call the backplane over here, hopefully a low latency network. And this is what you can see in the memory blades. This is what we have been looking at, basically. You have CPUs and you have some memory modules. And if you want to have even more memory, you essentially can attach a memory blade, which is designed purely for memory access. You can see that there are lots of memory. There's lots of memory over here, so that you can extend the capacity. And you have some memory controllers and engines or simple processors to enable access to this memory, essentially. Okay, so this is very interesting. Clearly, this is needed to support very high memory capacities. You could do this similarly to storage as well, but we'll not go into that. But you can see that there's local memory in the CPU, and then there's remote memory that the CPU can access in this memory blade. And there could be another memory blade that's far away. So memory hierarchy can extend further and further, where the same trade-off that we discussed, that required us to go to a hierarchy exists. Basically, it's the latency capacity trade-off, right? As you go farther from the processor, the latency increases. As you go farther, the capacity also increases. And that's the purpose of the memory hierarchy in this particular, well, in general. Okay, so there are a lot of interesting work that's going on. This is one work that we've done. If you're interested in this, there's a lot of research that needs to be done in this area also. Okay, so that was to push your limits, if you will, limits of thinking, critical thinking. And you can think critically and say, okay, how much memory we can have in our servers going into the future? How much of it is wasted? There are a lot of interesting questions over here. But now let's go back to our toy cache example, because I want to cover some of the basic design decisions before we move further to more complex ones. So this was, remember our toy cache example. We actually built a toy cache that was direct mapped. And you know what direct mapped is. Just to remind you, a given main memory block can be placed in only one possible location in the cache. And this was our representation of the direct map cache. And then we showed that this direct map cache is not good at handling conflicts, because if two cache blocks happen to map to the same memory location, and if you need both of those cache blocks in an interleaved manner, cache block A, B, A, B, A, B, A, B, that's your access pattern, and they happen to map to the same location in the cache, you cannot house more than one block in that location, in that index, as we've also discussed. As a result, you get a 0% hit rate. And to solve that problem, we made this cache set associative. And remember, this was the idea. Again, I won't go into detail because we covered this a lot. Essentially, you have two locations that a block can map to in a cache. Basically, blocks with the same index can map into two locations. Right? And then we said that, okay, this may not be good when your access pattern is ABCD, 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 and they all map to the same location or same index. Again, you get a 0% cache hit rate. So we increase the associativity to 4-way, making the cache more complex, as you can see. And then in the limits, your associativity is fully associativity, meaning there is no indexing that's going on. You just compare the tag of the address to the tags that are stored in all possible locations in the cache. Clearly, this is the most flexible. This eliminates all of the possible conflict misses because everything, in a sense, everything conflicts with everything else in the cache because there's no, everything maps to any possible location in the cache, right? So this is the most flexible organization, but you can see that the trade-off is that it's expensive. It has many comparators, large muxes, and we've discussed all of this. And this was the last slide that we covered in full. And I made a joke of this graph, saying that this is a perfect industry graph. Whenever industry shows you something, they don't tell you the numbers of the axis, as you can see, right? But the purpose of the graph is not to really read the numbers. It's to show the trend. As you increase the associativity, hit rate increases, but at some point you get diminishing returns, as you can see, right? Your hit rate is increasing very, very little as you keep increasing associativity, averaged across many workloads. For a given workload, this curve may be different, of course, right? So basically, higher associativity is in general good, but at some point, your returns diminish. And also, as we will see today, as you make your caches higher associative, you need to manage the cache in a more complex way, because a block can map to any location in the cache, and many blocks content for those locations in the cache. Let's assume that you have 1 million locations in the cache. When you actually want to bring a block into the cache, you need to decide which other of the 1 million minus 1 blocks you're going to evict from the cache. And that decision is much more complex now, because you have 1 million blocks in the cache. That decision is much easier if you had only 2 blocks that you're considering. You're bringing 1 block into the cache. Which other of these 2 blocks that you're going to evict in a two-way set associative cache? Right? So basically, some of the decisions become much harder, much more complex as you increase the associativity of your cache. Okay, so this is where we stopped last time. I said we were going to talk about issues in associative caches. But let me give you a framework of what we're going to talk about for some time. And we're going to talk about a lot of other design decisions and caching as well. Basically, when you bring a block and when you access a block, you can think of each block in a set as having a priority. Priority is importance of the cache block, let's say. How important is it to keep the block in the cache? We're going to talk about what does that mean later on. And the key issue in cache management, set associative cache management, is how do you determine and adjust the priorities of the block, essentially? So there are 3 key decisions that you make in a set. And this is actually isolated to a set because the set of blocks that map to that set are managed together. They don't conflict with the other blocks that are in different sets, different indices. And these can be categorized as insertion, promotion, and eviction. What happens when you insert the block into the cache? That's the first one. Meaning when you fill the cache with a given block. A block is coming from memory or some other cache level. What do you do to the priorities? You could change the priorities. For example, the least recently used management policy says that whenever you bring the block into the cache, make it the highest priority, meaning the least likely to be evicted or latest to be evicted into the future at this point in time. That's one management policy. Is that a good policy? We will talk about that in a little bit. So basically, insertion actually discusses, encompasses where to insert the incoming block. It also, you can also decide not to insert the incoming block. There's another management decision you make over here. If there's some information that you may have for some reason that says this block is not going to be reused into the future at all, don't insert the block into the cache. Basically, if this block doesn't have locality, temporal or spatial. The question is, how do you get that information? Of course, modern systems actually have a lot of predictors, hardware predictors. In hardware, you make a prediction as to whether this block is going to be used into the future. How do you make that prediction? That's more advanced. But you can imagine with history, right? We've seen branch predictors. You can actually have similar predictors based on history that try to decide whether to insert the block into the cache or not. And this is fascinating. This exists in these machines. This machine is already doing something like this at that general level. Programmer can actually say, this block is not going to be reused, as far as I know, and can give a hint using a load instruction. These are called non-temporal loads. And that hint can be used by the cache to not insert a block into the L1 level. You can do this actually in Intel processors today, as we're going to discuss actually next time using prefetching. So that's one decision that you make. Promotion is the decision that you make when you access the cache and you get a cache hit. And then the question is, how do you adjust the priorities of this block that you hit on and all of the other blocks that you didn't touch in the same set, right? Do you change the priority of the block? how do you change the priority of the block? It's actually not easy, basically, because that gives you information. That cache gives you information. That cache may give you information that it may be a reinforcement that you're going to access that block again. That depends on the access pattern. If the access pattern is such that you think that the reinforcement is correct, then maybe you increase the priority of the block that you just accessed, right? That's the idea of the least recently used mechanism. So least recently used management policy says, whenever I hit on this cache block, I'm going to make it the most recently used, and that priority is the highest. Meaning, I expect that block is going to be accessed again and again and again next time. So you increase its priority. Again, that's not necessarily the best way. Another management policy is completely random. Whenever you hit on a cache block, randomly change the priorities. Could be interesting. And it turns out it's not a bad policy on average across many workloads, because in some workloads, locality doesn't exist very well, and you have set thrashing problems, etc. Okay, and the third decision point in a cache is when you are trying to evict or replace a block. Meaning, when you get a cache miss, when you're looking for a block in the cache, and it's not in the cache, that's a cache miss, then you bring the block, and then you have a bunch of blocks in the set. Now, if the set is full, meaning all of the blocks in the set are actually valid, then you need to decide which block to replace from the cache. If the set is not full, if there's some invalid block, meaning there's no data in that block, then the decision is easy, right? You bring the incoming block and make it valid. But if the set is full, you need to replace a valid block, and the question is, which one do you replace? And that's why this is called a replacement policy. Which block do you evict? And once you evict that block, how do you adjust the priorities of all of the other blocks? And so this is really a general framework, and all caches need to make this decision basically. All levels, L1 cache, L2 cache, L3 cache, L4 cache, DRAM, main memory. You need to make these decisions at all levels, essentially. And even they may or may not be completely or well documented, but there are decisions that are made at all of these points when you do something to a cache. Insert, promote, or evict and replace. Does that make sense? So now you clearly see that there's a huge design space over here, guys. How do you decide all of this? Usually there are simple policies that are used, but things are getting more complex today. So let's take a look at one of these policies, eviction replacement policy, but this also has some implications on insertion and promotion. So which block in the set do you replace on a cache miss? As I said, if there's an invalid block, that means there's no data over there, the tag is not valid, put the data incoming block there, right? That's easy. You're not replacing anything in that particular case. Assuming that there is no invalid block, which is hopefully the steady state of your cache, you consult something called the replacement policy. So what could be a replacement policy? It could be random, as we said. You randomly pick, if you have a 4-way set associative cache, for example, you randomly pick one of the ways and say, I'm going to replace that one. Okay, it could be first in, first out. It could be least recently used, as we're going to discuss a little bit more, because this least recently used makes sense from a temporal locality perspective. Remember, we motivated the caches saying that if we're going to reuse the data that we have used recently in the past. And if you touch something at this point, if you brought that in the cache, probably you're going to touch it again. That's the premise or the anticipation of basic cache. But this is not necessarily correct, right? This is a heuristic in the end. There's no guarantee that this will happen. And if this happens, then you're not going to touch any other data, in fact, right? This doesn't make sense to happen indefinitely in the end. But least recently used is a very popular policy. But there are approximations to this also, because this is not easy to implement, as we will discuss. So people, some processors implement not most recently used, or evict the block that's not the most recently used. Because least recently used requires keeping track of an order within the set, right? If you have a set with 4 ways, if you really want to truly check out the least recently used block, you always need to keep track of the order of use of all of the blocks within those 4 ways. And I'm going to ask you a question in the next slide, so you can start thinking about how many different orderings are possible within those 4 ways if you want to actually perfectly keep track of all possible orders and perfectly implement least recently used. we're going to see that it's going to be unsustainable with large associativities. So a lot of caches actually implement some approximation of it. And then there's the least frequently used. So do you keep track of frequency in the cache? That's another question, right? These are relatively simple still. Then if you actually incorporate some other metrics into your decision, like cost, what is the cost of a cache miss? And this is important because if you miss in the cache, and if you are going to evict a block, and if it's very costly to refetch because it's coming from very far away, let's say remote memory, this is a lot more expensive than a block that's easy to refetch, that's not coming from remote memory. So different cache blocks have different costs in terms of latency to refetch. And this should be taken into account in the cache management. Now, it becomes hairy in this case because you're not looking at right now, what am I going to access next? That's one dimension. Now we're also looking at how costly is it for me to bring the data into the cache. And this should factor into the decisions, as I will show you later in this lecture also with a simple and beautiful example, hopefully. This should factor into the decisions because, as we discussed, it's not just about the hit rate of the cache, it's also about the latency. So when you're managing the cache, you need to take that into account. And we'll put energy into it also later on. So it's a complex management decision. And we're just talking about a single cache. And then we're going to talk about the hierarchy soon. Okay, so we're going to talk about that. And actually, a lot of modern processors implement some sort of hybrid replacement policy that tries to get the best of both worlds. Remember the hybrid branch predictors that use different algorithms to cater for different types of branches? Hybrid replacement policies also exist to cater for different access patterns or different access patterns for different sets or within the same set also. These are some things we're not going to discuss in detail, but you can imagine these things. And then the question is, of course, what is an optimal replacement policy? People have tried to figure this out. This is very hard to define because there are many metrics, right? What are you looking for in terms of optimal? If it's about hit rate, maximizing the hit rate, there's an optimal that we will define. But it's not just about the hit rate, it's also the cost. So the optimal is very, very difficult to define in this case. Okay, any questions? Okay, let's take a look at a specific case over here, which is the least recently used policy. And it's really a management algorithm. It's not just an eviction algorithm. LRU, least recently used, is really a management algorithm of the cache, which answers questions about insertion, promotion, and eviction. We're going to look at the eviction part of it, but keep that in mind. And the idea here is very simple. The idea is evict the least recently accessed block. It sounds very simple to implement, right? Now, the problem is it's not that simple, at least if you have large, highly associative caches, because you need to do what is just written over there. You need to keep track of access order of blocks. So if you have 4 blocks, you need to keep track of in which order they were accessed in the past. Which one is the most recently accessed, which one is the next most recently accessed, which one is the next most recently accessed, and which one is the least recently accessed. So you can see that there's an ordering. And when you access one of those blocks, that ordering changes, right? You need to promote the block that you're accessing to the most recently used position or most recently accessed position. And you need to change the ordering of everything else that you did not touch. This is what I mean by priority. And with a 4-way set associative cache, it's not bad. But if you go to 8-way, 16-way, 32-way, 64-way, this becomes intractable. Well, intractable is very strong, maybe very hard to implement. Okay, let's start with a 2-way. Let's start with a direct map cache, actually. If you have a direct map cache, and if your management policy is least recently used, how do you implement that? Basically, you evict whatever is in the cache, right? Whenever you bring some block, you evict whatever is in the cache. So you don't need to store any extra metadata for this. So in direct map cache, there is no policy. Policy is applied to set associative caches. There is a policy, actually. You need to decide whether you actually evict whatever is there or not. So there's actually a policy over there also, but it's not really a replacement of whatever exists. Well, it's kind of a replacement still. So there's a policy, but that requires more metadata. Assuming that you don't do that, assuming that whenever you bring a block into the cache, you don't bypass the cache. You need to evict something and you need to make space for this block. You don't need any additional metadata in a direct map cache because that's how it is. But if you have a 2-way set associative cache, now you have 2 blocks in a set. and you're bringing one block. So what additional metadata do you need to implement LRU perfect? How many additional bits do you need to keep track of the ordering between these two different blocks? Anybody? Minimally. Yes. Exactly. Yeah. 1 bit to distinguish which one is the least recently used, and that if that bit is 1, exactly. Basically, you point to the way that actually is the least recently used or most recently used. Okay, so that's the minimal actually, 1 bit. You can actually do it with more bits, of course, but minimal is 1 bit. Okay, now let's make the question a bit harder. If you have a 4-way set associative cache, how many bits do you minimally need to implement LRU perfectly? Anybody? This is a probability question, actually. If you take a probability and statistics class, these are the questions that you answer over there. Thoughts? Yes. 2 total in the set per block. Yes. That is a correct answer, but it's not a correct answer to this question. That's what you would do if you want to, let's say, minimize your headache when you implement hardware. 2 bits per block enables you to specify which order you have per each block, right? But the minimal number is actually, so in a 4-way associative cache, basically you're saying it's 2 times 4, which is 8 bits, right? You need 8 bits. Yes. 5 bits. Okay, how did you get that? Absolutely, yes. So yeah, basically he did the probability calculation. You need 5 bits. Let's see if you can do this relatively easily without destroying the. So maybe somebody needs to help me with this. So can you see this on the web? If you can see this, I'm not going to switch anything. Maybe I'm going to stop share. What do you think? Is that better? Okay, I guess you can see it. So basically, you have 4 different blocks, right? Basically, you need to position these 4 different blocks. This is the 4-way cache. And you can think of this as LRU, and then next LRU, and then next LRU, and then the most recently used. There could be 4 possible things that you can place into the LRU position. Once you have placed it, there are only 3 blocks left in the N LRU position. And once you've placed it, there are 2 blocks in the next LRU position. And once you've placed all of those, there is only 1 block you can place into the MRU position. And basically, the number of orderings you have is the multiplication of these, because there are so many possible ways you can place those blocks. So it's 4 factorial. And 4 factorial, how many bits do you need to represent 4 factorial? Essentially, that's log 2 to the 4 factorial, which is 5. Log 2 to the 24, right? So that's good. Now, if you do this exercise for n-way associative, you get n factorial, right? And then the number of bits is log 2 to the n factorial. And this is actually pretty bad if n is large. So if n is 8, it's already bad. But if n is not 8, if n is 64, that's 64 factorial. How many people can give that value? What's log to the 64 factorial? I don't know off the top of my head, frankly, but you can put it in a calculator and you'll see that that's a huge value. And this is basically an encoding, right? You have 24 different orderings you can have in this block. And then you need to encode this. So basically you need to have some, let's call this ordering. And you have 5 bits over here. And then you need to feed this to a decoder to figure out which one is the least recently used, which ordering you are actually. Which way is the most recently used, which way is the least recently used, etc. So there's actually hardware complexity. It's a hardware decoder that determines which order do you have. So I think the answer with 2 bits is actually a bit easier to implement, because what you do over there is you attach, let's say, I'll do a tag key thing over here. You attach 2 bits to each block in the tag store, of course. And you don't need to do that decoding. And these 2 bits basically say, let's say 0, 0 is the least recently used. 0, 1 is the next least recently used. 1, 0 is the next least recently used. 1 is the most recently used. In this case, you don't need to do any decoding, right? You basically have 8 bits which is not the minimal, which is not, that's why it's not the answer to the question. The minimal is 5. But in this case, you don't need to do any decoding to figure out. You already know if the tag bits for the replacement policy say 0, 0, that way is the least recent. Right? You just need to look for that. Okay. So this is a trade-off in terms of, you always have a trade-off between latency and capacity. And this is another example of it. The capacity of storing the replacement policy bits is low in this case, but the latency of figuring out what you should really evict is longer because you need to go through that decoder. Here, the capacity of storing the replacement policy bits is larger. It's not the minimal, but the latency of figuring out what you should evict is actually much easier because it's already decoded, as you can see. Okay, so hopefully this gives you an example of why LRU is difficult to implement if your caches are highly associative. So we've answered a lot of the questions on this slide now. Okay, and things are presented online as well. Good. Okay, so I think we've already answered all of these questions. Yeah, we kind of also touched into the logic that's needed to determine the LRU victim, which is the least recently used. Victim is the block that you're going to evict, basically. There's this terminology that has been used. And if you repeat this for n ways at associative cache, you get the number n factorial orderings, and you need to, the minimal number of bits that you need to represent n factorial is log 2 to the n factorial. So this is why LRU is not scalable. That's why most modern processors do not implement true LRU, also called perfect LRU in highly associative caches, because in some processors we have 128-way associative caches, for example. 64 is very common, 128 is less common, but it exists. Actually, there are two reasons why processors don't implement perfect LRU or keep track of the perfect ordering. One is true LRU is complex. We've just discussed this. The second is LRU is already an approximation. It's already a heuristic anyways. It's not perfect, clearly. It's not the best possible cache management policy, essentially. And people have shown that there are other cache management policies that are better, as we will see soon in some cases. So what do processors implement today? At least for the LRU part, because they actually can be using different policies for different types of blocks, if you will. But not MRU, for example, not most recently used, is an approximation to LRU, right? It basically says, don't evict the most recently used blocks. Among everything else, pick randomly. That's one implementation of not MRU type of policy. So at least you protect the most recently used block in that case, right? There's a hierarchical LRU. Basically, you divide this set into hierarchical pieces, and you try to approximate LRU, or you do perfect LRU at some level, but then you don't do perfect LRU at higher levels of the tree in the hierarchy. Again, I don't want to go into the details of this because details actually vary significantly. I just want to give you the basic ideas of how you can approximate. And then there's also something called next victim replacement, and this is trying to keep track of, basically protect two things, let's say. Maybe you're trying to protect the most recently used and something else as well. How do you determine that something else? It depends on the policy. So most processors essentially don't implement LRU for these two reasons. Okay. Now let's go and look at another question, which I kind of foreshadowed earlier. You have LRU, which you can call principled, let's say, right? Because it's based on some principle, some anticipation that whatever you're going to access right now is going to be accessed next. But then there's another, let's say, principled approach, which is random. You randomly pick to something to evict. Right? You can say maybe the random is not principled, it's just random, right? But random could be principled depending on the access pattern. So which one's better? So let's take a look at an example. We have a 4-way associative cache again, and we have cyclic references to A, B, C, D, E. I think this is correct. If this is what you have, is with LRU, you get 0% hit rate. Right? This is called set trashing. You're trashing a single set, basically. You can only house 4 different blocks inside that set, but you're really accessing 5 different things in the worst possible access pattern for LRU. A, B, C, D, E, A, B, C, D, A, B, C, D, E. Right? So whenever you're accessing something, you're evicting the thing that you're going to access later. So you get a 0% hit rate. You can convince yourself with this. Yeah, basically the program working set in a set is larger than the set associativity. That's the definition of set thrashing. In this case, random replacement policy is a much better approach and a much more principled approach. You randomly pick which one you evict, and hopefully you're not going to evict something that you're going to touch in the cache. Right? And the probability of that is actually relatively low. That gets lower and lower as associativity increases. Okay? And you can do the calculations if you want to get the hit rate, but it's going to be much better than 0%, let's say. Does that make sense? Okay, so this is why random replacements actually make sense. When you have thrashing that occurs, you can actually detect the situation with simple mechanisms, right? You can actually detect whether you're getting a 0% hit rate, and you can switch to random replacement policy. That's one of the things that we have evaluated many times, and we've shown that that's a better idea than just keeping on having 0% hit rate. Okay, so in practice, performance of replacement policy very much depends on the access pattern. And I just gave you an example. If your access pattern is this is the worst case access pattern for LRU. It's much better for random. Yeah. And the average hit rate, it turns out, if you average across many, many workloads, average hit rate of LRU and random are similar. This also shows that set thrashing happens a lot in real workloads. Of course, it depends on your associativity, but with associativity like 8, 16, 32, it happens a lot. Okay, so best of both worlds is basically having hybrid replacement policies. LRU is good for some access patterns. Random is good for access patterns that are not thrashing the cache. And how do you actually put them together? Essentially, you keep track of which policy is doing better by sampling some sets and sampling what would be your hit rate if you actually implemented that policy. You could do that actually in hardware with very low cost. I'm not going to get into the details. And then you follow that particular policy in the remaining part of the cache. You could do this at different granularities, at different parts of the cache, but you could also follow a single policy globally based on the sampling that you do in some sense. Okay? But you could also follow a different policy locally at different indices based on the sampling you do in every set. Okay? Of course, the latter one, the local policy per set is much more expensive in terms of hardware because you need to sample actually a lot more in that case, but it's possible. So I find this fascinating actually, and there are many implementations of set sampling that happened, especially in recent years. But if you're interested, you can take a look at this paper, which I'm going to talk about at some point to talk about something else actually, not this. Okay, any questions? Okay, let's talk about the optimal replacement policy because this is an interesting question in general. And this was well defined for miss rate, if you will. There is this thing called Bellidy's OPT policy. And the idea is to replace the block that is going to be referenced furthest into the future by the program. That sounds great, right? The question is, how do you actually know this? Knowing this is the problem. This is not implementable. People have actually tried to approximate this using some access by tracking access patterns. There's some work in this direction, but this was first proposed a long time ago for virtual memory systems. So how do you implement this? It's basically it's unimplementable. How do you even simulate this? When you're actually simulating a program is actually not that easy to know about also. But if you want to do some interesting project, this is something you can think about. So, okay, is this optimal for minimizing miss rate? Under some assumptions, yes. I'm not going to go into the proof of it. You can read papers about it. Now, the interesting question is not this though, because miss rate is only part of the equation, right? We also talk about miss latency, which is execution time, right? What we really care about is not the miss rate of a particular cache or even the cache hierarchy. It's really how long do I take to execute this program if I'm concerned about performance, right? It's not the miss rate of a particular cache. Those may be interesting to examine if you're having problems locally, but in the end, the bottom line is how long does it take for me to execute this program? And if this is the question, then the answer to this question is this is not optimal for sure, because it doesn't take into account the cost of a cache miss, the latency of a cache miss, basically. Not all cache misses are equal, and I will show you some examples of this, but I've already given you an example, right? If you can fetch the block quickly after you evict it, assuming you need it again, that is a not so costly cache miss. If you cannot do that, if you need to wait for, let's say, I don't know, seconds to fetch the block because it's coming from some remote memory for whatever reason, then it's a much more costly cache miss. And if your replacement policy does not take this into account, it may evict the block that's costly to refetch. And as a result, it may actually destroy your execution time. Okay. Yeah. So basically, this is this is one reason where the miss is serviced from, local or remote, which cache hierarchy level. And then we're going to see an example of miss overlapping, which is an interesting thing, which is going to segue us to the next lecture as well. Okay, and then I'm going to talk about this paper because this paper actually introduced some of these ideas. Okay, so I'm going to get back to this. But let's talk about some of the other design decisions. Right now, we've covered some things and we went a little bit deeper, but let's pull back and talk about some other design decisions that we have. So we've talked about the tag store, right? We have a val bit in the tag store. We have a tag. This was the basic cache. Now, if you have a set associative cache, we added the replacement policy bits that we just discussed. But there are other things that you can have. This is the dirty bit or the modified bit. Essentially, do you keep track of whether or not a block is modified in the cache? Now, this goes to another design decision, which is, is your cache write back or write through? Meaning, whenever you do a write to your cache, do the write propagate immediately to the next level, or you keep the modified data in the cache and you propagate the writes, or you propagate the updated value to the next level after it's evicted, after the block is evicted. And this is a very fundamental design decision. I'm going to talk about handling writes in the next few, let's say, minutes. The key question is, when do we write the modified data in a cache to the next level? Write through means at the time the write happens, all caches or the next level gets updated. Right? Write back means when the block is evicted. So this classifies caches into two different categories. You can have write back cache and write through cache, and they have clearly different trade-offs. Write back cache, you can combine multiple writes to the same block before eviction. So these are called write combining. This is called write combining. Basically, you have a block and you keep writing to this block, right? Either to the same bytes or different bytes, it doesn't matter. You keep writing to it. And if you actually don't write to the next level, what you're doing is you're combining all of those writes in the same block in this particular level of the cache, and you write back all of those combined writes into the next level when the block is evicted. Right? That's the advantage of a write back cache, write combining, if you will. This potentially saves bandwidth between cache levels and saves energy. If you propagate every single write to the next level, you're basically wasting bandwidth, right? Because there's some bus between the caches, and you're basically keeping that busy. That bus may be used for something else, and clearly you're wasting energy potentially. So of course, the downside of the write back cache is additional complexity, right? You need to have this extra bit in the tag store indicating that the block is modified or dirty. These are two terms that are used actually in caches. And we will see it in virtual memory also in the next lectures. So this is the trade-off. Write through cache is simpler design because you don't need to keep track of this, let's say, dirtiness, and also you don't need to write back when is needed. But of course, I'm going to talk about this positive later on. But of course, it's more bandwidth intensive, and there's no combining of writes. There's another benefit of a write through cache, which will become a little bit more clear when we talk about cache coherence very briefly in this lecture. How many people know about cache coherence? Okay, some people. How many people do not know about cache coherence? Okay, that's what I would expect. More people would raise their hands. So we're going to talk about cache coherence. Cache coherence is an issue that happens when you have multiple processors, and each of them have their own private caches. Hopefully, at the end of this lecture, we'll get to it, or maybe early in the next lecture. And when one cache writes to a cache block, that is also a cache that one processor writes to a cache block that's cached locally, and another processor needs to has the same cache block cached. What happens, right? You have some inconsistency in the values because you've written to this local cache, but the other cache is not updated. So this is the cache consistency or cache coherence problem. Now, if you do write through, this problem is a lot easier to handle because whenever you do a write, all of the other caches are updated essentially, and you don't have the cache coherence problem as bad, if you will. If you do write back, unfortunately, this problem gets amplified because the writes that you do locally as a processor don't get seen by some other processor to the same cache block. So write through caches are actually simplifying the cache coherence design, but they have other downsides, as you can see, right? Bandwidth intensive, etc. As a result, a lot of the caches today are write back. There are some cases where you have write through, but write through is not very common today, especially due to the importance of bandwidth as well as energy. Write through is being avoided most of the time. So today, you should also consider energy in the design decisions a lot. That was not the case, let's say, 20, 30 years ago. Okay, so let's talk about writes a little bit more. Writes actually add a lot of other interesting things. Do we allocate a cache block on a write miss? So basically, you do a write to a cache. For a first level cache, this could be a store. And you miss in the cache. You bring the block from memory. Do you allocate it in the cache or do you not allocate it? Meaning, do you evict something else from the cache? Now, this is actually a general design decision, but with writes, it becomes a little bit specialized. Because writes may be considered a bit more special than reads, right? Because writes are not on the, you can tolerate the latency of writes more easily because whenever you do a read, there should be some dependent instructions probably, right? With writes, you usually don't have dependent instructions following them because you're writing to some value in memory. Maybe you're going to touch that many number of cycles later, but not soon, hopefully. So basically, there are two design decisions that you make over here. You allocate on write miss or not allocate. Now, if you allocate on a write miss, what may happen is you write the cache block into the cache, and then you may have many updates to that cache block. Right? So if that happens, this is good. You can combine the writes basically instead of writing individually to the next level, right? If you allocate. So that's the upside, right? Combining again, very similar to the previous one. And this is also simpler because write misses can be treated the same way as read misses, assuming that you're also allocating a block into the cache whenever you miss on a read request, like a load request, as opposed to a store. Okay, the downside is it requires a transfer of the whole cache block to the cache if you actually want to allocate on a write miss. Now, no allocate essentially is opposite. Basically, you can do the opposite of these things. But it also has one advantage, which is it conserves cache space if the locality of written blocks is low. So it can actually give you a potentially better cache hit rate. Of course, the downside is it's not able to combine, right? So it really depends on what kind of access pattern you're seeing to the cache. And that's really the key that I want to get over here, that I want you guys to understand. The access pattern is the most important thing into the cache. If the access pattern is such that you don't need write combining, but you actually need to conserve cache space and the locality of writes is low, then no allocate on writes is actually a better design decision. And again, you can have hybrid policies over here. This is easier to implement in the sense that you basically need to decide whether you actually put the cache block into the cache or not put the cache block into the cache or not even fetch the cache block to begin with. You just need a predictor to decide which access pattern you're seeing. And this is I said this is easier than, let's say, what we discussed, hybrid replacement policies, if you want to have a hybrid policy over here. But it requires you to detect the access pattern, which may not be that easy. So a lot of the current processors try to use heuristics to detect the access patterns and try to decide what to cache and what not to cache and make some of these decisions. More recently, people are looking at the machine learning techniques to actually discover or predict these things in a much better way and with limited success. So let's see. Okay, let me give you one more thing about the writes. This is actually trying to handle the write combining issue. So assume there's an access pattern where the processor writes to an entire block over a small amount of time, like streaming through the block. And the idea is basically you have a 64-byte block. Let's assume that you write to every single byte. The first 8 bytes, the next 8 bytes, the next 8 bytes. So you do it for every 8 bytes. So 8 bytes you write. Then the question is there any need to bring the block from the cache to from the memory in the first place? You've completely overwritten the block. You didn't read anything out of there. If that's your access pattern, there's no need to bring the cache block, right? You can just create the cache block inside the cache and then write it to memory. Does that make sense? Of course, this doesn't work well if your write granularity is smaller than your cache block granularity. Today, as we discussed, the cache block granularity is 64 bytes. Write granularity, store word, as you've seen, is 4 bytes, right? Or 8 bytes, let's say. You can have 8-byte stores also. That's much smaller than the cache block granularity. So how do you implement this? So basically, the idea is sub-blocking. Simply write to only a portion of the block called a sub-block. For example, 4 bytes out of 64 bytes. Right? Now, the problem is what I just said, the granularity mismatch. You have valid and dirty bits associated with the entire 64 bytes. And if you write only 4 bytes, and if you don't have the remaining part of the block, you have a problem. Right? So what do? Well, sub-blocking. Replicate the valid and dirty bits with the sub-blocks. So associate valid and dirty bits with sub-blocks. Or the general idea is divide a block into sub-blocks. This is also called sectors. And have separate valid and dirty bits for each sub-block or sector. And allocate only a sub-block or a set of sub-blocks on a request. So whenever you do a write to a sub-block, you basically set the valid bits, set the dirty bits, write the data, and of course set the tag over here. And all of the other valid and dirty bits are 0. So this way, you don't need to bring the cache block into the cache, right? Because you're just writing to a sub-block, and that sub-block is not going to, you just modified it. Right? You don't need the old data that was there. Okay, hopefully that makes sense. So the huge benefit of this is no need to transfer the entire cache block into the cache. You can just write to a sub-block, and then you can write back the sub-block, modified sub-block later on, and then merge the data. So that's good. A write simply validates and updates the sub-block, basically. Now, there's also another benefit, because now you have more freedom in transferring sub-blocks into the cache. A cache block does not need to be in the cache fully. We kind of reduced the granularity of management. The granularity of management was 64 bytes. Now we actually are doing 4 bytes at a time, because that's our sub-block granularity. And whenever you fetch something, you just fetch whatever 4 bytes you may need, or whatever, let's say, which pattern of 4 bytes that you want, let's say, assuming you know that, assuming you can predict that. So this gives you a lot of flexibility right now. Now, the granularity is interesting because the block is still at the granularity of 64 bytes, right? So we did not change the size of the tag. That's the benefit of sub-blocking. You just increase the valid and dirty bits, but you do not have, this is the difference from having smaller blocks. So the question may be that, okay, instead of having 64 byte blocks, why don't we have 4 byte blocks, right? If you have 4 byte blocks, your tag size increases a lot more. Here we kept the tag size the same, but made sub-blocks. Yes, we paid the penalty of additional valid and dirty bits for each sub-block, but the tag size did not increase, okay? Okay, so basically, this gives you more flexibility in management because you can decide how many sub-blocks and which sub-blocks do you transfer on a read as well, on a read request, as well as a write request, clearly. Of course, the downside is more complex design. You have more valid and dirty bits. And clearly, based on the design decisions that you have, you may not exploit spatial locality fully. But the good thing, if you have a streaming write access pattern, if you start from the beginning of the cache block and write 4 bytes to the beginning, 4 bytes to the next one, 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 you populate the entire block inside the cache, and you don't need to read anything from memory or the next level. So with streaming writes, this sort of design shines. But it also has a lot of other flexibility, as I discussed, that can enable much better cache management. So a lot of caches are actually sub-blocked today. Okay, let me give you one more design decision, and we'll take a break. So there are a lot of other design decisions, instruction versus data caches, for example. Do you keep them separate or unified? Do you have both instruction and data in the cache at the same time? Well, if you have them unified, let's take a look at their pros and cons. The big pro is you dynamically share the cache space between 2 different types of, let's say, data, instructions and data. You get better overall cache utilization, meaning there's no over provisioning that might happen if you actually partition the cache into instruction versus data. Right? So we'll talk about that later on, actually. But if you partition the cache to have separate instruction and data, let's say you have 64 kilobyte instruction cache, 64 kilobyte data cache. If your instruction working set is only 1 kilobyte, you're wasting 63 kilobytes of the 64 kilobyte instruction cache. If your data working set is 127 kilobytes, you're thrashing your 64 kilobyte data cache, even though you had actually additional 63 kilobytes in the instruction cache that you cannot use because they're reserved for instruction. So a combined cache of 128 kilobytes can actually much better service a 1 kilobyte instruction set plus 127 kilobyte data set, right? Because combined, they're 128 kilobytes. Okay, that's basically the effect of better overall cache utilization. Now, of course, the downside is instruction and data can also evict and thrash each other. That, I gave you a very good example. What if you have a worse example where the working set together is much larger than the cache space? Now you don't have guaranteed, let's say, space for either instructions or data. As a result, this may actually hurt your pipeline a little bit. Some data can evict the instructions. But again, if you have a unified cache, you can potentially manage it. But the real reason why at least the L1 caches are separated between instruction and data in modern processors is this. And it's dictated by the pipeline, as we have discussed in the last lecture. Instructions and data are accessed in different places in the pipeline, right? Remember, we formed the pipeline processor. You fetch the instructions in the beginning of the pipeline, and then you do stuff in the pipeline. And then you need to fetch the data for some instructions. So these two things happen far away in the pipeline. So that makes actually a lot of sense to have separate instruction and data cache so that you can have fast access integrated into the pipeline stage where you actually need to fetch the data. And this is the reason, this is the main reason why instructions and data caches are separate in modern processors. So basically, because of this reason, first level caches are almost always separated because of the pipeline constraints, but outer level caches are almost always unified. So L2 cache, there's no distinction between, there's no separation between instruction and data. In your management policy, you can actually take into account instruction versus data, but that's a different question. Okay, so let me cover this also, and then, okay, and then we'll take a break. Actually, I take it back. This is a good place to take a break because I have a lot of things to cover in the multi-level cache design and management. So let's take a break until 15:20, and then we're going to come back and talk a lot about multi-level cache management afterwards. Oh. Yeah. Good question. I don't remember what we have done. We should probably send an email to the digital technique. Yeah, I think it should be okay. I have a problem with that, right? Just that. Okay. Yeah. In the alternative is the driving.
Ja, dat is met een greenscreen.
Yeah, exactly.
Oh ja, dat is een andere.
Okay, with it, but send the question. At least the location will make a statement.
Was it so this song?
You know on the website also.
Hi. Hello. You wanted support?
Oh, okay.
No. To ask about the camera from.
Yeah, I think yes, he had a problem feeding the camera. I don't remember. I didn't check, but
so we use this web here for the
yes.
Zoom meeting. So the problem was if we use this as a cam, we couldn't project this laptop's screen to do this.
Maybe it's okay. We solved the problem right now with this, right? This
Yeah, right now.
Yeah, maybe we should not change it because it's a lot of.
Afterwards, we can.
Yeah, maybe afterwards you can take a look. You explained the problem, right?
Yeah.
So
let's not touch
it. That's good for us.
Yeah, this is working. Yeah, but I think he had some problem in the beginning projecting that. Yeah.
Should not be. Don't know. So it's simple as this. That the camera is on this.
Yeah. But I use this one. So I click this one.
No.
But
this is not for you.
Oh, this is not. I
Use simply this one. Yes.
And
then you select the camera from this.
Yeah. AVIO MK or something like this. Yes.
You need it only for a picture from him. Not for details or not for black hole.
For me, like as a webcam of this one.
Yeah.
Like in the USB.
You can select it here. So first select here cam speaker. Yeah. So you are sure that it is this one. Then you can set here.
Actually, I did this.
You have seen how it works here.
Yeah. I did this like before, but today it's different.
Okay.
I did the same procedure.
Yeah.
This one, but let's say the camera.
Yeah. But you have to try it again.
Okay, yeah, maybe.
So you should be able to use it like a normal cam
I see, yeah.
So
Yeah, I did it before, but today, yeah,
you
maybe.
should be able to select that.
Okay, okay.
And then select here the
Yeah, but the configurations are okay right now, right? You don't need.
yes,
Ah,
yes,
okay.
exactly.
Yeah, okay.
And
You already have
this
a
is-
number generator for some reason.
It's for insane.
We do
So
have-
it's, totally independent.
Okay, yeah,
And on this side, you make
yeah.
the normal configuration
Yeah,
as when you don't use camera.
okay.
So that's all.
Or you can try it this way.
I'll do the same things next time. Yeah. Yeah. Yeah.
But then
Thank you.
question is, how do you-
Oh, you're welcome.
Yeah.
Or
Yeah, fine.
otherwise you can ask us that we can
Hello? Yeah.
to help
Can you
you
hear me?
with setting up
I think we need to.
if you want. So
Okay.
just
Maybe you
make a
do-
mail, then we can make
Yeah.
I checked it before as well.
appointment.
But the room is not connected, right?
Yeah.
So can you take a look at this?
Yeah.
Yeah, right now it's MacBook Air. It'll be Extron. I mean, the microphone is not
And
there.
otherwise,
Okay, I see. Yep.
Yeah. Can you fix
Plugged
this?
in, right?
Yeah, but it's not. I think you'll have to see it, right? We have a problem with the microphone. Somebody complained online.
Yeah, but I tried it. It was okay.
Yeah, for me it works as well. Like I hear you. Like,
Maybe when those people come, can you check? The microphone's okay right now? Let's test it.
I tested.
Yeah, but you don't see it with the microphone, right? Okay. But why do we not see it over here? Sorry. I mean, we see the speaker, right? Extron, but why don't we see the microphone?
Ah, here is.
It's MacBook Air right now. That's not very good. So that's the problem I see. So it's not connected there.
But
We're testing the microphone, don't worry. Yeah. Can you check that? Because we normally see that. Yeah, there's Extron HDMI also in the microphone, right? Maybe I can answer your question.
how we build the single which is live and then we set the viewer.
The sub-block?
Yeah.
Yeah, you basically
Drive it.
right to that, and then make it to dirty and valve.
How does the valve work? So how do I don't know, a subject is 10 bytes large and now
Should we remove it?
all the check is after the
So this one is plugged in. Where is the? Okay.
the purpose of it is to when we
Okay, we don't have enough ports now.
but we just start writing this up. But we don't have to load it at all from memory because we have done all the writing. How do I keep track if it is half ready? Or half ready? If only the
So it
first 10 bytes are recently written, the other ones are unknown. How do I
So basically, you need to check all of these valves separate. The design.
So I don't want to break the camera right now.
Maybe
So I don't want to
more
remove.
clear. You see what I mean? Whenever you write something, you write sub-block or multiple sub-blocks. Whenever you want to access something, you need to check whether the sub-block that you're accessing is valid.
cannot write less?
Yes, there's an audio.
Right,
Where's the audio?
Yes,
Okay.
then you need to make it, you need to make out more valid so that a finer.
So the subblock is determined by the visibility size. So if I have find less in memory, the subblock is a byte. That's fixed.
Not necessarily. I mean, you can say a sub-block is, let's say, 4 bytes. If you write 2 bytes, then you need to bring the sub-block from memory. The remaining 2 bytes.
Because if I do smaller write, I just give up.
Exactly, just bring some of the, at least a sub-block. But you don't need to bring the entire block.
No, it's a
Just
machine.
Okay, but if I write the whole block, then I say that it's valid and I don't catch any.
Exactly.
But only if I write.
This is the one, right?
You can, whenever you're doing your writes, you don't need to write something, you see
What?
all of the writes. You write the sub-block. Let's assume that the writes is the same ground note as the sub-block, and you make that valid. And you don't need to fetch the remaining sub-blocks. Remaining sub-blocks don't ever need to come into the cache.
Yeah, the problem right now it's an adapter to an adapter, right?
Subblocks into
Maybe it's not a problem. I don't know.
No, that has to be still part of the.
We could
yeah,
test
exactly.
this
What we're talking about is
basically here.
essentially.
Yeah, I
smaller
think we
blocks.
can do
So if
that.
I write.
But like this
two
can no
large
longer
enough
use it.
write, then we can say, okay, all these
You need to
subblocks,
use.
we don't have to memory, they're just valid from all.
Yeah, exactly.
And I want to ask about the hardware before that we have. But you want to keep track of the communication. So basically.
What I can do is plug this here and plug the camera.
Can you plug
Exactly.
it again?
No, but it's an adapter to an adapter. That's why it's not working.
But try
No,
it
no, I
again.
have a specific permutation and it access the first element of the permutation.
Yeah.
The logic is very complex to get the next.
Yes, that's why we see.
Yeah, but the problem is the microphone, right?
Yeah. Like when we connect it, we could able to see also the camera
Yes,
thing. Yeah.
yes, that's true. So should I remove it from here?
Exactly, yeah. So it's not that simple to decode it.
So it's just very complicated.
Well, it's not a, yeah, exactly. So basically you need to encode the different audience in different ways.
Which permutation state and then you.
Exactly. I mean, it could be a lookup table depending on. Not very fairly right, it's not very good. You don't basically bring data to the cache. Yeah, you use the prediction. Or it could be a design.
I don't see it.
You never know. That's no allocation. But if it never ends.
Yeah, no, I.
Well, you do this.
So if I believe that I won't need it in the near future, then I don't know.
Exactly. Okay, can you hear me now? We had some microphone issue. It's interesting. We always have some of these problems. Okay, at least you can hear me here. Is online okay also? If you could check that, that'd be good. Okay, this is where we stopped. I mean, I give you a lot of design decisions. I'm going to give you more design decisions, as you can see. As you can see, this is a fascinating area, but it also shows you the complexity. Now let's talk about multi-level caches. Multi-level cache design and management actually makes things more complex because so far we've been talking about the design decision at a single level. At a single cache, you have many, many design decisions, some of which we did not cover. But when you go to multi-levels, you need to manage the hierarchy holistically as well. And that introduces a different set of constraints and design decisions that you need to make. And one of the key things that I want to emphasize is the first thing that's written over there. Cache level greatly affects the cache design and management. The policies that you employ are basically dependent on which caches we're talking about, L1, L2, L3, L4, main memory. They're all dependent on where they are, basically. And we've seen some examples of this, right? In the last lecture, I said, for example, L3 caches have high capacity, their latency is not as important. As a result, you can play circuit tricks to make the density a lot higher over there and maybe trade off, meaning make the capacity higher at the expense of some more latency because it's long to access the cache anyways. Everything okay? Okay, so let's take a look at another example of this. First level caches, second level caches, and further level caches. We said that first level caches are partitioned the instruction and data because of their level, because they're serving the pipeline, right, immediately. So they're partitioned. And in general, in the first level caches, decisions are very much affected by the cycle time and the pipeline structure itself. Because you need to get the data very quickly into the pipeline, instructions are especially more important, actually, because instructions, if you don't get the instructions in a pipeline manner quickly, you'll stall the entire pipeline, right? Data is also important in the back end. But basically, these are usually smaller, lower associativity, and latency is critical, as we've discussed. A design decision, for example, you have the tag store and the data store. And we said earlier that in our basic cache, tag store and data store, we access them in parallel, right? We index the tag store, we index the data store, we get the tags and data in parallel, we do the tag comparisons. If there's a match, we use the data that we actually accessed concurrently with the tag store. If there's a mismatch, then we discard the data. Now, you can do this in parallel in the first level. And first level is small, and first level hit rates are high. So it makes sense to access the tag store and the data store in parallel. Now let's take a look at the second level. Second level, you're not as bound by the pipeline constraints, so your access latency is less important. It's still important, of course, but your hit rates, you need to balance the hit rate and access latency. So usually these are large and highly associative. Latency, again, is not as important. So one design decision in the tag store and data store is to access them serially. So you have the tag store, you have the data store. Instead of accessing them in parallel, you first access the tag store, and the tag store indicates whether it's a hit or miss. If it's a miss, you don't access the data store. You saved a lot of energy. That's nice, right? And if a cache is highly associative, your data store is expensive to access because you're accessing a lot of things. Or if your cache is large, your data store is expensive to access. Now the downside is if it's a hit, if the tag store indicates a hit, you need to access the data store after that. So there's some additional latency. But that access may be easier to do also because when you get a hit in the tag store can also tell you which way of the data store you just need to access, right? You access only that way and not the remaining n ways or n-1 ways where n is your associativity. So basically, if you do serial access to the tag store, you determine whether it's a hit or miss and which way you hit on first, you save a lot of energy regardless at the expense of some latency, of course. So that's the trade-off you're making at the second level. And second level, tag store and data store can be accessed serially, and depending on the design decisions and how big your second level is, in modern processors, they're accessed serially. But now if you go to the next outer levels, where your cache is, let's say, 48 megabytes, 64 megabytes, even larger potentially, access energy becomes an even larger problem due to the size of the cache. And tag store and access data store are usually accessed serially to save energy in that case. And access latency is less of a problem at that point because you already waited so long. Maybe you can wait another 5 cycles, right, from the processor's perspective. So that's the trade-off, basically. Outer levels are very different from the inner levels. Inner levels are closer to the processor. Everything is dictated by latency and access time, whereas outer levels, less so. Another thing in the outer levels is the hit rates of outer levels are actually lower than hit rates of the inner levels on average, again. As a result, it usually doesn't make sense to access the data store in parallel with the tag store because many of the accesses you're going to miss anyway in the cache. So you should really avoid those large data store accesses. And data store is really the large part of a cache. Okay, so that gives you another example. Another design decision Hopefully that's clear. Any questions? Okay, another design decision is serial versus parallel access of cache levels. So parallel means that you access the next level in parallel with the previous level. So whenever you start the access of the previous level, you also start the access to the next level. This is a form of speculative access, right? It basically is useful if you miss in the first level, of course, in the previous level. So this gives you faster access to data if previous level misses. Hopefully the next level hits, but of course you can generalize it to n levels hierarchically, right? Now the downside is if the first level hits, if the previous level hits, you have unnecessarily access to the next level. You should stop that access or ignore the data that comes out of the next level, right? So this is a trade-off basically. It's a latency energy trade-off again, but unnecessary accesses waste energy, but they also waste bandwidth from the cache, so they're not necessarily good. But if you do the accesses serially, meaning next level is accessed only if previous level misses, you have slower access to data if previous level misses, clearly, because you start the next level's access only after you figure out that it's a miss in the previous level. But the upside is you have no wasted access to the next level if previous level is a hit. So the serial access, actually, usually people employ serial access. We're going to talk about when you may employ parallel access, hopefully tomorrow a little bit. But usually in the cache hierarchy, you employ serial access unless you have good reason to believe that you may miss in the cache, for example. If you do serial access, next level does not see the same access as the previous level, right? So this actually adds another dimension to the management. Now, the first level cache sees all of the accesses coming from the processor. Next level doesn't see all of the accesses because you don't expose those accesses. Only the missing accesses from the first level are seen by the next level. The next level, only the missing accesses from the second level are seen by the next level. Basically, fewer and fewer accesses are seen by later levels. Now, this has implications. Essentially, a previous level is acting as a filter. It filters some temporal and spatial locality. So the locality that's seen in the access pattern is very different across different levels in the end, which means that management policies should be different across different levels, and they are different. This is one of the other reasons why cache management policies differ across these different cache levels. Okay, so I'm going to talk about a little bit more, but just to put this into perspective, there are clearly L1 and L2 caches over here, but these folks have decided there's a system level cache that's shared by the GPU, CPU, and accelerators also. So clearly there are other decisions that you make at the other outer levels of the cache hierarchy, right? If you look at L1 and L2 caches, they're relatively tightly coupled to the cores over here. But once you go to the outer level, you also go out to the system. Right? Once you're out at the system, you actually have other stuff that may be sharing data across each other. As a result, you may actually want to have caches that are shared across different types of processors as well. So it's important to keep that in mind, actually. Essentially, once you go outer and outer, you're far away from the processor and you're out in the system, and there's other stuff that you need to consider, if you will. Okay, so this is just to give you some examples that we've seen earlier. And also, it also shows that how big these things that we're talking about is. So this is the reason why L3 caches are not accessed in parallel in terms of tag store and data store. You access the tag store first and data store next, because this is a huge cache, as you can see, right? You don't activate a huge amount of your chip just to get data that you're going to miss on anyway, that you're not going to need anyway. Okay, so and this is true everywhere. Okay, let me give you some other things. I'm not going to talk about this in detail, but I decided that we would use some real examples. So in some cases, the programmer can decide to bypass caches. I mentioned some prefetch instructions or non-temporal load instructions earlier, but in this particular case, in an NVIDIA GPU, A100, for example, you can bring data from L2 cache directly to the scratchpad. You basically bypass L1 and register file, which used to be there in the past. So you can use some instructions that directly bring data from L2 to scratchpad. So basically, the programmer actually can have some control over the caches or the scratchpads, depending on what instructions are exposed. So if somebody asks you a question, are caches part of the microarchitecture or the ISA? Then the answer is probably it depends, right? It depends on whether the programmer can manage the cache or not. Okay, so I'll give you another example. In later NVIDIA incarnations, H100, for example, you could actually take the data directly from the global memory to the shared memory, which is essentially the scratchpad in NVIDIA terminology, bypassing the L2 caches. So you don't need to bring the data into the L2 cache. Again, this is under programmer control. You can also move the data from a scratchpad of one multiprocessor to another multiprocessor, again, under program control. So basically, there are a lot of other design decisions that we're not going to tackle. And this is an example, right? What do you expose to the programmer, right? If you expose more, will the programmer do more? If the programmer is an expert, perhaps, but maybe not all programmers. And you can see the relative sizes over here, right? The L2 cache, 60 megabytes, and this is 80 gigabytes, and shared memory, I think we had the number earlier. Okay, so let me give you at a high level, what are the other design decisions, some of the things that we're not going to cover. Which levels do you place the block into? Whenever you fetch the block from memory, for example, which levels do you place the block into? L1, L2, L3, all of them, a subset of them? That's a good question, basically. Modern processors can use predictors, for example, for that, but this could be done under programmer control as well. Which levels do you evict the block to? If you're evicting from an inner level, which outer levels do you put it to? Do you put it directly into L2? Well, depends. Maybe are you going to reuse it soon? Again, if you can predict that reuse patterns, maybe you don't put it anywhere. Right? You basically say, I think I'm done with this block. I'm not going to touch it for a long time, so I'm going to drop it. It's not modified, for example. It's not dirty, meaning I can drop it, right? I don't need to do anything with that because the copy is already up to date in memory or somewhere. Okay, so bypassing versus non-bypassing of levels actually is important. Essentially, that's what we're talking about. Which levels do you bypass? Which levels do you not bypass? There's a huge design space over here. And then there's the other design decision, which is called inclusion in memory hierarchies. Your memory hierarchy can be inclusive, exclusive, or neither. This is called non-inclusive. And there are all kinds of processors that implement these different types. Inclusive means a block in an inner level is always included also in an outer level. So basically, L1 is included. The contents of L1 is included in L2. The contents of L2 is included in L3. Essentially, these are inclusive. And this simplifies cache coherence, actually, which we're not going to go into. Exclusive means that a block in an inner level does not exist in an outer level. So this is strictly exclusive. So inclusive, the downside of inclusive is you have data duplication, right? L1 has some data. L2 also has the same data. L3 also has the same data in L2. So you have a lot of data duplicated across the hierarchy. You're not really utilizing the cache space very efficiently. If you say exclusive, whatever I'm going to have in an inner block is not going to be replicated anywhere else, or basically a block can be present only at one level. Then you're actually using the entire cache space in a much better way. But it turns out inclusive is easier to implement coherence, whereas exclusive is a bit harder to implement coherence, because if you do inclusion, you just need to check the later level caches or some level caches for coherence. Okay, and then there's a non-inclusive, which says basically, I'm not going to enforce either of these. A block may be replicated at some level, or it may not be replicated. I don't keep track of this. I don't enforce it. My coherence protocol is not going to depend on it. So it's going to happen. So this gives you design freedom. Let's say this relaxes the design decisions. In exclusive hierarchy, you need to ensure that no other cache has it. In inclusive hierarchy, you need to ensure that every other outer cache has it. In a non-inclusive hierarchy, you don't need to care. You can basically bring some data and some other cache may also have it, fine. As long as you keep it coherent and consistent, no problem, right? So, okay, there's more to talk about in this design decision also, but I gave you the basics, hopefully. But now you can see other dimensions also, right? When you go to multiple levels. Okay, so let's talk a little bit about cache performance. We've kind of been implicitly talking about this, but I want to cover a couple of things that are important. So there are a bunch of cache parameters that we've discussed. Even the management policies, if you actually add the multi-level management policies, you can add them over here. But cache size, block size, associativity, the management policy within a single level, as well as management policies across levels. All of these affect performance. We're going to not look at performance. We're going to look at hit-miss rate because it's easier to reason about. Let's take a look at the effect of cache size on cache hit rate, as you can see in this industry type of graph. Again, no numbers. So basically, cache size is measured as total data capacity. Usually when we refer to a 60 megabyte cache, you don't include the tag store. You always talk about the data store. Tag store is some extra, could be kilobytes or megabytes, whatever, on top of that. But basically, if you have a bigger cache, larger cache, you can exploit temporal locality better. And this kind of shows that, right? As cache size increases, your hit rate increases, and you get diminishing returns at some point. Again, averaged across many workloads. Different workloads will behave differently, as I will show you soon. If you make the cache too large, clearly this affects the hit and miss latency adversely. Bigger is slower. We know that very well by now. If you make the cache too small, it does not exploit temporal locality very well. Useful data is replaced often, basically. So there's this notion of working set, where the entire set of data the executing application references, within a time interval, of course, may be present in the cache. So where your hit rate saturates is when your working set fits in the cache. So if your cache size is a little bit larger or equal to your working set size, you don't expect your hit rate to increase further by increasing the size of your cache, essentially. Hopefully this makes sense. Of course, working set of a program it has a temporal component of it as well, right? At a given point, you're working on some data, as we will see later on, actually. We're going to take advantage of that also. You would like to keep the working set in your cache as much as possible, essentially. Okay, so benefits of larger cache actually widely varies. It depends on the size of the working sets, for example. I'll give you some examples over here. So this is real data measured in some paper, as you can see over here. This is the number of ways from a 16-way 1 megabyte L2 cache. So if you actually use only one way for this application, the hit rate, or misses per one, this is the miss rate, misses per 1,000 instructions, the miss rate is the same as, almost the same as, when you use 16 of the ways for that application. Basically, if you increase this, in other words, if you increase your cache capacity by 16 times, it doesn't matter. For this application, the miss rate doesn't change. Why? Because of the access pattern, it's not benefiting from a larger cache, at least within that range. So this is an application where the utility of the cache is low. Another application, you're increasing the cache size from 1 divided by 16 megabytes to 1 megabyte, 16x, and you see that there's a huge decrease in the cache miss rate. So this is an application that benefits a lot. And another application, you can see that after you increase the cache size by about 5x or 6x, you don't get any benefit because your miss rate is almost zero. Right? Basically here, this is an example where your application fits in the cache and larger cache doesn't benefit the application. This is a saturating utility. Application has saturating utility from larger caches. So you see all kinds of behavior like this. These are the three major patterns of behavior that you would have in larger caches. But again, it's very application dependent. It's very access pattern dependent. Okay, so let's talk about block size. We talked about associativity earlier. I'm going to talk about the slide again, but I'm not going to go into that in detail. But block size is also important. Block size is the data that's associated with an address tag, as we know. Now, this is the curve that you get as you increase the block size, assuming you keep the size of the cache constant, data set size, because you have to keep something constant, right? So if you have two small blocks, oh, sorry. I should also mention that block size is not necessarily the unit of transfer between the hierarchies. If you do sub-blocking, for example, you transfer sub-blocks between the different levels, etc. So I'm ignoring sub-blocking, etc. in this graph. We're just looking at blocks, no sectoring, no sub-blocking. So if you have two small blocks, each block doesn't exploit spatial locality well because the block is smaller, 8 bytes, for example, or 1 byte, let's say. And you have larger tag overhead, clearly, right? So basically, that's why your hit rate is low. And as you increase the size of the blocks more and more, you exploit spatial locality better. And you reduce the number of blocks you have, of course, in the cache, assuming your cache size is constant. So at some point, your performance starts reducing because the number of blocks you have is small, becomes smaller. So if you have two large blocks, which is at the other end of this curve, you have too few total blocks. As a result, you do not exploit temporal locality well. So assuming your cache size is constant, larger blocks exploit spatial locality as you increase the block size, but you reduce the number of blocks you have in the cache as you increase the block size. As a result, now you stop exploiting temporal locality really well, because in the limits, you have a large cache, 1 megabyte cache and 1 megabyte block. That's a single block. You'd better have extremely good spatial locality there, right, to exploit that. And also we'll talk about some other issue with large blocks soon. Basically, large blocks waste cache space and bandwidth and energy if spatial locality is not high. And also you need to bring the large block to the cache, right? If you have 1 megabyte block, it takes a long time to bring the 1 megabyte block to the cache, because remember the memory interface we had was 64 bits. Right? You need to fetch that 1 megabyte block 64 bit at a time from memory. Of course, you can widen the interface with techniques that we've discussed, but it's not going to be you fetch all of the 1 megabytes at a single shot. Okay, so large blocks, basically this is, I foreshadowed this point. Large blocks can take a long time to fill or to place into the cache. So what a lot of processors today do is they do a critical word first, assuming you know this information. At the first level, for example, you know the information that, oh, this load requires this word in this block. So you try to fetch that word first from memory and bring that first, as opposed to the entire block. So you prioritize basically what you fetch within the block. So supply the critical data to processor immediately. But large blocks can waste bus bandwidth, and sub-blocking actually solves this problem partially, essentially. Sub-blocking has this advantage, as we have discussed earlier. Essentially, by associating the valid and dirty bits for each sub-block, you just need to bring the sub-block to the cache. If you're reading a location within the sub-block, you just need to bring that sub-block, right? You don't need to bring the entire block into the cache, basically. You can bring the remaining parts of the block lazily, let's say, over time, potentially, if you think they're going to be useful based on some prediction mechanism that you have in the processor. Okay, so we talked about sub-blocking. We know when it's useful, but clearly it can be useful in implementing large blocks without having to always pay the penalty of fetching the large blocks into the cache. Okay, associativity, we've already seen this graph, so I'm going to skip this, but I will handle this question. Maybe someone can answer. So basically, we know that larger associativity has benefits and diminishing returns. Smaller associativity is not good for hit rate, but hit latency is important, so it enables lower latency. But a fun question to answer is, do you need a power of 2 associativity? Anyone? Can we have a, let's say, 5-way associative cache? Or 3-way associative cache? Who says yes? Yes to a 3-way associative cache. Okay, good. Who says no, we cannot have a 3-way associative cache? Okay. Okay. People who say no, let me show you that I can make a 3-way associative cache. This is a 4-way associative cache. Nobody has a problem with this. We constructed it. How do I make it 3-way? Well, I get rid of this, and that's 3-way. And nothing changed. So yes, you can have it. I'm not joking, you can have it, this works, right? Basically, there's no reason to have a power of 2 associativity, because associativity is not about indexing, right? You don't use the address to index into a set. You really do this comparison. So if it's a 3-way associative, it doesn't matter. Whatever matches, you take. As long as this logic is correct, as long as you figure out which one is hitting, you can have a 3-way associative cache. You just don't use the other possibility over here, right? You just don't use one of the inputs of this mux, essentially. Make sense? Okay, so hopefully you'll convince yourself if it doesn't make sense. But this is our 8-way fully associative cache. Well, how do you make it 7-way? Get rid of 1. This is my 7-way. If you want to make it 9-way, well, you need to widen the mux to 16, unfortunately, but you waste, you can add 1 more, essentially, right? Okay, so basically associativity is not dependent on anything in the address being any power of 2 value, basically. Okay, let's talk about classification of cache misses. By the way, I should say that there were caches that were implemented in real processors that were 3-way, because they found out that that was the way to actually fit the blocks into their processor. I think HPPA had some cache that was 3-way, let's say. Okay, let's classify the cache misses. We're going to add coherence miss later on, potentially, if we have time, but cache misses can be classified into 3 categories. This is important because this determines actually how you can reduce the different categories, or this gives you insight into that. Compulsory miss, capacity miss, conflict miss. Compulsory is, this is the first reference to an address. Whenever I talk about an address, I'm talking about a block address from the perspective of the cache. Always results in a cache miss. This is compulsory. You cannot eliminate it with just caching, right? So subsequent references to the block should hit in the cache unless the block is displayed from the cache for these reasons. Either it's a capacity miss or a conflict miss. So capacity miss, cache is too small to hold all the needed data, basically. It's defined as the misses that will occur in a fully associative cache with optimal replacement, which may be hard to define. Well, for hit rate, it's easy to define. For execution time, it may be hard to define, of the same capacity, essentially. Essentially, defined as the misses that are not compulsory and not conflict misses. You can think of it that way. But basically, this is a valid definition that doesn't incur the conflict miss in it. Defined as the misses that would occur even in a fully associative cache with optimal replacement of the same capacity. Basically, you do whatever you do, you don't have a conflict miss, and you still get a miss that's a capacity miss. And conflict miss can be defined this way. By the way, this is not a circular definition. Conflict miss. This is the definition of how to eliminate conflict misses over here. And then after that, you can define the capacity miss. And conflict miss is basically, you cannot classify it as a capacity miss or a compulsory miss. Essentially, you don't have a fully associative cache and you have a miss in the set. Well, you probably have a problem with the conflict over there. If you don't have a fully associative cache, basically, by definition, it's a conflict miss, essentially, if it's not a compulsory miss. Okay, so how do you reduce each miss type? Compulsory, caching only access data doesn't help, basically. Because caching says, I access the data, I'm going to re-access it again, I'm going to cache it. So you need to do something else. Unit can have larger blocks. Larger blocks can actually eliminate compulsory misses that occur with smaller blocks, right? That's possible. But what we're going to discuss tomorrow, prefetching actually helps. The idea is to anticipate what you're going to need next and prefetch into the cache, as opposed to waiting for the processor to access it. Why don't you just anticipate? The processor is accessing blocks in a streaming manner. Address A, A plus 10, A plus 20, A plus 30, A plus 40. Whenever I access A, I say, oh, I should bring A plus 10, A plus 20, A plus 30, A plus 40, A plus 50, all of those blocks into the cache also. That's the idea of prefetching. And we're going to see that. How do you eliminate conflict misses? More associativity helps over here, clearly. But there are other ways to get more associativity without making the cache associative. And there are a bunch of stuff that we're not going to talk about in detail. There's a victim cache, better randomized indexing into cache, better utilizing the cache, and software hints like we have seen earlier. I'm going to talk about some things a little bit later. Capacity misses, how do you actually eliminate that? You utilize the cache space better. Basically, keep the blocks that will be referenced. So management of the cache actually helps with the capacity misses. And we're going to see some software management soon. Basically, you can divide the working set of a program, as opposed to requiring a program to work with a huge working set, divide it into smaller pieces, and those smaller pieces hopefully fit in the cache, and you arrange the computation such that computation happens on smaller pieces of data at a given time, such that you don't get cache misses while you're doing that sub-computation that you have divided the bigger computation into. So we're going to talk about that. So there's actually a lot of things that have been done to improve cache performance. And the main thing is main goals are actually three. There are three fundamental goals. You want to reduce the miss rate, you want to reduce the miss latency or miss cost, and you want to reduce hit latency or hit cost. And some of these go against each other, unfortunately. So reducing miss rate is good, assuming you don't increase the miss latency or miss cost, for example. We will see that. Reducing hit latency or hit cost is not easy in software, let's say. But essentially, all of these can be influenced by software, especially the miss rates to some extent. So we're going to see some software management very soon. But don't ever forget that all of these above together affect the performance. It's not just about the hit rate or miss rate. It's also about the miss latency, miss cost, and hit latency or hit cost also. Okay, so these are some things that you may see if you take an advanced course. How do you reduce the miss rate? How do you reduce the miss latency and cost? And how do you do the last one that we're not going to talk about? But let's talk about some software approaches before we move into some other examples. So I've already given you some examples of better replacement and insertion policies, management policies, but we've not talked about software as much. If you know that caches exist, as a software designer, you can actually do a lot. Let me give you some examples. You can restructure your data access patterns such that they're friendly to the replacement policy, for example. They're friendly to the set associativity, for example. You don't trash the sets. They're friendly to the cache size. You can restructure your data layout. And there are a bunch of techniques. We're going to talk about blocking first. Okay, so how do you restructure data access patterns? The idea here is very simple. You either destructure the data layout or the data access patterns. So let me give you an example over here. Assume that you have a vector x, and you store this vector in a column major order. Basically, what does column major means? Consecutive, well, it's part of the matrix, let's say, sorry. It's not a vector, it's matrix, as you can see. It's a two-dimensional vector. In other words, two-dimensional matrix. Basically, if it's stored in a column major order, if you remember from the SIMD lectures, consecutive elements in the column are in consecutive location in memory, right? In other words, xi plus 1, j is the column index, follows xi comma j in memory, right? These are consecutive in memory location. So that's good. Ideally, these are in the same cache block, basically, because the same cache block is in the same spatial space. Whereas xi comma j plus 1 is far away from xi comma j, assuming this is a large matrix, right? Assume that that's a large matrix to begin with. Hopefully that's clear. This is the column major. We've seen this actually multiple times in SIMD lectures. So basically, given this, I would argue that this is very poor code. If you actually know that your cluster is a cache, which all clusters do today, you should not write this code, assuming your matrix is stored in column major order. Why? Basically, the inner loop over here is iterating over the columns. What it's doing is essentially is touching xij, and then xij plus 1, and then xij plus 2, xij plus 3, ... Basically, it's touching other columns, right? So you can fix this relatively easily by doing a loop interchange. You interchange the inner loop with the outer loop, and you still get the same sum, as you can see. Basically, this is much nicer. What you're doing is consecutive iterations of the inner loop is touching consecutive locations in memory, right? That's the idea over here. Okay, so this simple fix will actually buy you a lot of performance in real life. Of course, you need to know that there's a cache and this happens, right? Now you know that there's a cache and you can actually make your code much faster. So you should never write the poor code. But of course, this requires the knowledge of the data layout as well as the access pattern. So you need to think basically. It's not as simple as, okay, I write this code and it's beautiful. Okay, so let's call loop interchange. There are other optimizations that can increase hit rate, like loop fusion, array merging, etc. Compilers could be able to do this actually if they can disambiguate nicely, but it may not always be possible. Okay, let's take a look at another example, blocking. I've already given you the idea actually. Here, the idea is to divide the loops operating on arrays into computation chunks such that each chunk can hold its data into cache. It's kind of basically divide your program into smaller chunks such that the data that each chunk is operating is in the cache, right? It doesn't have cache misses. Now, this avoids cache conflicts between different chunks of computation. Essentially, you divide the working set such that each piece fits in the cache. At any given time, you're operating on different parts of the working set. This is also called tiling, loop tiling, or blocking, or matrix blocking, matrix tiling. There are many names for this. I'll give you an example from GPU, real code. You can actually watch a longer lecture from an earlier incarnation of this course. Essentially, we have same memory location accessed by neighboring threads. You can, for example, apply a Gaussian filter on every pixel of this image. If you're actually doing computations, if this is too big to fit in your cache, just do the computations that you need to do over here in a batch, and then you move to the next part, right? And then you move to the next part. That's the idea over here. So basically, to take advantage of data reuse, you divide the inputs into tiles that can be loaded into scratchpad memory into GPUs, but it could be a cache also in a CPU or even a GPU. And tiling is basically dividing this entire, let's say, matrix into smaller chunks, where the size of the smaller chunks is smaller than the size of the scratchpad or the cache. Now, let me give you a real example. If you have matrix multiplication, you have matrix A, you have matrix B, you're multiplying A and B. Whatever you're doing is essentially a dot product of this vector row of this with this column, and you're generating the data point over here, right? Now, assume that these are in row major layout. If both of these matrices are in row major layout, while you're doing this axes, this has good spatial locality clearly. So the cache hit rate of these axes are nice. Unfortunately, the cache hit rate of this is really terrible, as you can see, because things are far away from each other. So basically, if you naively implement this using the entire matrices, you have poor cache locality for multiple reasons. One is what I just said, and also the size of the matrix may be very large. Essentially, the consecutive accesses to B are far away from each other in different cache lines. Every access to B is likely to cause a cache miss. So how do you reduce that impact? Essentially, you can achieve better cache locality by dividing each of these matrices into tiles or blocks that fit in the cache. It could be the cache, actually. It could also fit in the scratchpad or the register file. Right? So let's take a look at an example. So assuming your tile sizes are determined to be this, such that this fits in the cache, this fits in the cache, this fits in the cache, and actually they all together fit in the cache. You should determine it that way. You can have very good locality over here and here. So, and then you move to the next blocks, right? So you basically do the computation of the points over here, all of the rows, all of the columns over here, and have some partial sum over here. And then you move to the next tile and calculate these points. And then you move to the next tile and calculate the same points and accumulate, basically. So the hope is that you're maximally utilizing your cache space because you've determined the tile sizes such that whatever you're operating on, these 3 different tiles from 3 different matrices are in the cache at the same time, and you don't get cache misses. Makes sense, right? If your matrices are large, clearly you're going to get a lot of cache misses in this. Of course, this requires more work. Basically, this is the tiled implementation. You can see that the loop iterations are divided into tiles. Basically, you operate on sub-matrices as opposed to the matrices. And hopefully, these sub-matrices fit in the cache, scratchpad, register file. You can optimize for different levels in the hierarchy also. Okay, so that's basically what you do. You multiply small sub-matrices over here. Okay, if you want to know more, there are actually lectures that cover this in more detail, but we don't have time. Now, let me give you another example. So I've given you a lot of software examples so that you can actually do this. I'm going to give this example and then we're going to stop. But let's take a look at this example. You have a node. Assume that you have the database of people, and this is a linked list in this particular case. You have the name of the person and the school of the person. These are character arrays, as you can see. And you want to traverse this database. Let's traverse this linked list. Assume a huge linked list, 1 billion people in the world, all of the people in the world. Nobody should program like this, clearly, but assume that it happens. So basically, you're given a key, the name of a person. You basically check whether the node matches that input key. If not, you go to the next node. Basically, you're searching for a name in the entire, you're searching for a key essentially in the entire, or it could be the ID of the person, for example, right? You're searching for the key in the entire linked list. And if you actually find the key, find the ID, let's say, you print the name and school, for example, okay? Now, since we don't have time, I would normally ask this question. Does this code on the left have poor or good cache hit rate? And the answer is it has terrible cache hit rate because of this. So what you're doing is, let me take a look at, this is frequently accessed, and the other fields are actually not frequently accessed. So the frequently accessed data is blue over here. The likelihood of the key matching in this 1 billion accesses is very low, essentially, assuming you have unique keys. So this is not frequently executed code, not frequently executed data. So key and next are actually the frequently accessed fields, but name and school are not frequently accessed. So what do? Essentially, what we have done over here is with this data structure layout, all of these are in the same cache line, assuming a node is allocated spatially. It's allocated in consecutive locations. Next comes, this is maybe 4 bytes, int is 4 bytes. Now you have 256 bytes name. And your cache block can be 64 bytes. So most of your cache block is actually name, if you will. The key and the next is only a small fraction of your cache block. So while you're traversing this, you access one node, and then you get a cache miss to access the next node. So every node incurs a cache miss, basically. Okay? This could have been worse, actually. The layout may have been next and key may be separated from each other. So every node gets 2 cache misses, essentially. So basically, other fields occupy most of the cache block, even though they're rarely accessed. That's the problem. So the key idea is very simple. Once you realize that, what you do is, as a programmer, you could separate the rarely accessed fields into a data structure and pack them into a separate data structure. So these are the frequently accessed fields with a pointer to the rarely accessed fields, for example. And now you access 2 different data structures. Rarely accessed data structures here, frequently accessed data structures here. There is a small not frequently accessed component. The general idea is basically separate the hot data from cold data. Hot data is frequently accessed, cold data is rarely accessed, such that they're not in the same cache block. That's the key idea. Okay, who should do this? Programmer in this case, but compiler maybe, hardware maybe. Who can determine what's frequently accessed is a great question, which we're not going to answer. Okay, so we're done. We're going to pick up from here tomorrow and talk about prefetching, etc. I'll see you tomorrow.